ये क्लाउड में कर दो तो बेटर जाएगा कुछ यहाँ पे कर सकते हैं तो ड्रॉपबॉक्स डाल दोगे कोई 2 GB डालना ना फ्री में होता है STCS के साथ ये क्लास okay guys, so we'll start again. Any questions, any points discussed? You were saying something.
Yeah, actually, I was trying to the last example that you have given. I found it very interesting in one way. If so, when we define the dynamics in cycle by only a single rotation, theta irrational. But in this case, if we take the compactification of the 0-1 interval, and I am defining the dynamics in a such a way, take any point x in that, and t and x equals to snx plus x.
SNX.
SNX. Yeah, where SNX is the partial sum of the harmonic series up to n term.
Sorry.
So that way you have defined.
Shall we discuss it offline then? It sounds like it's kind of.
Yes.
We can go later.
Yes.
Okay. Yeah, just run it on. Yes. Okay, sure. So, Daksh, can you hear me?
Yes, yeah.
Where's the camera? It's here somewhere. Okay, good. So we'll take this.
Yeah, sure.
But you got the point which I was saying. Now you're speaking about it. Just make it non-overlapping. I didn't mention that, but if you make it non-overlapping, then each point is only linguistic once.
When you will send the notes?
Huh?
When you will send the notes?
I shared the notes, no? Last time.
It's very hard to study and
In WhatsApp.
I thought on WhatsApp I sent it, no?
Yeah, like there are actually two groups. So the one which Anirban created and one which I created.
But
So everybody is joined to 5 groups.
yeah, no, so that's true. But I must have sent it to the same group when I gave the homework, no?
I think got
You got the homework at least, right?
Yes, yeah, so I've got the homework. It's very hard to study out of the notes.
Achha, I thought I had submitted, so I'll do it after this class. Yeah. No, of course it's hard to study, but right now you have a homework from a book. So if you study from the book, you're set.
Can I explain the relay notes?
Huh? Yeah, that's
By the
fine.
next class.
Just do it on your own, doesn't matter. You can take a few more days.
By your next class?
That's fine. That's fine. No, yeah, we have to discuss the next class now. So let me do this also offline. Guys, the plan is as follows now. So next week, there'll only be a single class on Friday. So there won't be a class on Wednesday. And the Friday class will be by Anand Deo. I requested him to give 2 classes on extreme value theory. Okay, so you don't know extreme value theory, right? So it's good you learn a new area. It's about maxima basically. How to the maxima. Just like for sums, we have central limit theorem. Then you ask yourself, if I have maximum random variables, what can I say about them in the limit as that goes to infinity? So there's a whole theory on this. It's very nice because nowadays in climate change, etc., people worry about extreme events. Or for example, in 1952, Netherlands had this perfect storm, and they had this massive kind of sea waves which came inside Netherlands. I think 50,000 people died, lakhs and lakhs of animals died, etc. So after that, they had to make dikes. So Amsterdam is below sea level, and they have like massive dikes to prevent the waves from coming in. So a lot of mathematics went into kind of how high should the dikes be. So that's where extreme value theory kind of got impetus. Extreme value theory is used a lot in finance, insurance, and all that, but it got further impetus in this setting. And now, for example, they're worried with climate change, global warming, how much more the dikes have to rise. They want to basically keep it at a height so that the bad things happen 1 in 10,000 years. So, so how do you get good guarantee? So extreme value theory is very useful in that point of view. So rare events basically. So he'll give 2 lectures. Okay, next Friday and then one after that. Then we'll carry on with my lectures. Somewhere in
I was talking. So I don't think that any of us who are attending your course is taking lectures of logic. And mathematical logic has only 1-2 slots. There is no clash with that.
So what are you suggesting? What timing is that?
So it's around 2 to 3:30. So I don't know, means if you're free on that time, then we can, this is we are doing in a seminar time also.
Oh, you're saying Wednesday also we do it 2 to 3:30.
I don't know, means I can.
So that's a suggestion to everybody. Suppose we go for 2:30 to 4 on Wednesday. Then it's uniform, right? Wednesday and Friday. Does that work for everyone?
Yes.
Okay. So on the online also, right?
Online algorithms is there.
So let's do this then. From now on, we do 2:30 to 4, Monday, Wednesday and Friday. I think that's a better time, right?
On Wednesday, online algorithms course is there, which I'm auditing.
On
2 to 3:30.
Can you say-
There is online and.
Oh, there is online.
Yeah.
Okay, okay. Okay, then we can't do that.
Are you on Tuesday? Tuesday and Thursday 2 to 3:30.
No, Tuesday I'm teaching other classes.
I see.
You get to.
I see. Because that's
This time is okay, right?
yeah, this time is okay.
This time is fine then, right?
This
Means
time.
you are saying another class Thursday or
Oh,
the next week class?
no, I'm saying there'll only be one class next week and then we'll find.
The seminar for climate change, the seminar.
No, so what I'm saying right now is that rather than having 2 classes next week, we won't have a class on Wednesday. We'll just have a class on Friday at the usual time, 2:30 to 4 on Friday. But that'll be taken by Anandio.
Okay.
See, that's all I'm saying right now.
Yeah, sure.
And then you'll take one more class Wednesday afterwards, and then after that, I'll resume. And then towards the end of the month, I requested Shubhada to take 2 lectures on weekend budgets. Yes, that's the plan right now. What you should do is somewhere in mid-March or so, just start finalizing one paper or topic that you want to prepare and present. Okay, and then you run it by me. So we'll have that discussion. We'll schedule your talks, but we'll schedule it outside the class.
Yeah.
Right,
One
outside.
more thing I want to ask.
Yeah.
So is this course can be taken as a course qualifier?
Yeah. Okay, sure. Okay, yeah, so I'll send you the lecture notes. Okay, so now, okay, so later on, I just complete the discussion. I won't prove it right now. We'll prove it later when we have enough proofs. The proofs become much simpler when you have the right proofs. So remember, we had said that okay, we have mu of A is equal to integral f d mu on the set A. The f is measurable function, non-negative. Then you have the okay, mu of A implies mu of A is equal to 0. Mu of A equal to 0 implies mu of A equal to 0. And so in that case, we call f as, f is just a function. So the another notation for that is it's d mu by d. It's just the Reynolds-Nicotin derivative of measure nu with respect to measure u. This is notation, but all we're saying is it's a non-negative variable, which when you plug it in here, this way, I mean, you can almost see that d nu by d mu means that d mu cancel, d nu over set A gives you mu of A. So it makes an intuitive sense. The Reynolds-Nicotin theorem says that the reverse is also true, the converse is also true. That if you have 2 measures on the same property space, 2 measures mu and mu, such that mu of A implies, sorry, mu of A equal to 0 implies mu of A equal to 0. For all A events. So meaning if mu of A is positive, then mu of A had better be positive. Right? Then there exists a density function f such that mu of A is equal to integral f of d of mu.
So in the first case, aren't we saying f equals to that quantity almost everywhere?
Yeah. So in the integration, whenever I define the quantity, so if if f and g are almost surely the same,
Yes.
they'll be the same integral value.
Yeah, I'm saying about the when you are giving the notation f equals to d mu by d.
Almost surely.
Almost sure.
In the sense, anything else which is also almost surely equal is also satisfied.
Sorry, dv by dv is this is the definition, right?
Hmm?
So dv by dv is that a random variable.
Yeah.
Right?
It's a random variable defined up to an equivalence class.
Okay.
You know, it's all the random variables which are almost all equal can be called as equal. So in this case, yeah, this f is called d mu by d mu. So it's a real-time variable. So it's guaranteed basically. Now, okay, you say, okay, that's a big theorem, right? All you got was mu a equal to 0 implies mu equal to 0, and then how do you get this f to exist? It's a very nice existence result. On the other hand, if I told you that, okay, you know, suppose my mu of a is on the real line is given by some g of x dx, x belonging to a, or x could be in a Euclidean space. So mu has a density, mu is a probability measure of the density of x, and mu is a probability function with density. Let's call it f of x dx. Right? Suppose mu and mu have this property. Often we had come up with this probability measure right on the Euclidean space. Multivariate Gaussian on the way. Now suppose I tell you that okay, fx equal to 0 implies gx equal to 0. Suppose f and g have this property. For example, f and g will be positive on the whole of the space. Then this will be true. Then of course I can always go back and write mu of a is equal to integral x and a g of x dx. And I can divide and multiply by f of x. Right?
So zeros of a is a subset of zeros of g.
What's that?
Zeros of a is a subset of zeros of g.
That's right. Yeah. Well, you're not dividing by 0 basically. That's the whole point. Right. What do I want to say here? A is F D. Yeah, so that's right. So this is basically equal to x is A and x. Fx dx is just d mu x, right? So I can just call this as d mu x. I mean, you can directly choose. So your nx is the density function, is the Radon-Nikodym derivative of nu with respect to mu, and that's just equal to g of x upon f of x. So it's not entirely surprising, right? All you did was you multiplied and divided by the density function. And you could do that because you're not having dividing a positive number by 0. And whatever I'm saying in continuous setting, you can say in discrete setting. So when you see this, then you say, okay, this has to generalize. And that's what Radon-Nikodym theorem achieves. It's, you know, it's to be expected. You know, why should not be true? This stuff you probably have seen in important sampling. You've heard this stuff before. Right. So yeah, this change of measure ideas. So this change of measure, like you express the quantity under another measure, it's used now everywhere. It simplifies calculation dramatically. In large deviation theory and sampling, point sampling, much of mathematical finance relies on kind of change of measure ideas, but in complicated spaces. Here's no theorem is very famous. And the Q1 is the Q1 is also. You learn a lot. Your BTech was in the computer science or?
Electronics and communication, EC.
Then you would have like it. Maybe, yeah. Even then it's quite stressful. Yeah, no, it's. I think I've seen classes before the students were doing so much. That's good. Certainly Gazdal server was very good. And okay, so this is what we have here. Now let me move on. Let's see what I have. Okay, now Jensen's inequality everybody knows, right? And LP is the LP norm is monotone NP that you know already. It just follows from Jensen's. So I don't have to show you that, right? So when Jensen, if I have a convex function, and this is because okay, my function is convex. I have a convex function. I have a random variable x. Somewhere it will have an expectation, e of x. At that point, I'll draw a tangent to this function here. That's always below this, right? So then that tells you that okay, phi of random variable x is greater than equal to. So what's the equation of this tangent? What is this? A of x plus b, right? So some a and b. And now I take expectation on both sides, so I get e of x. A of e of x. That's equal to phi of. That's all there is to this. And then we have that, okay, so I define my LP norm of a random variable x. So I collect all these random variables where this norm is finite, and that's my LP space on UFP. Right. And now the claim is that suppose so x belongs to, let's say, LP2 implies that x belongs to LP1 or 1 less than P1 less than P2 and x P1 is less than equal to x. So I'm not paying attention to guys. If you have any questions, any issues? All right. Malhar, I can't see you. So whenever you're ready. Okay. Right. So this proof is not true. All is it clear? How to prove this? But let me just illustrate one point. Because we have to prove existence of P1 norm also. We just know existence of P2 norm. We don't know existence of P1 norm here. So that needs to be proven. So one argument that works always well, works very well and good to know is this idea of truncation. So I just define my
exists by that means satisfies continuity.
what's that?
By exists, you mean emphasize satisfies?
I just mean that the pth moment exists.
Oh,
Just the pth moment. P2, in this case, P2 exists. So I don't know if the P1 moment exists. We kind of know it must be true, but let's just kind of complete argument for it. So what we'll do is we'll look at this truncated variable, right? Truncated variable, not truncated. The point is now it's bounded from above by n, so it's all the moments exist. P1 moment exists and P2 moment exists. Now we look at this function in this case, phi of x would be x bar P1 by P2. Right? P2 by P1. So it's convex. So then we get okay. So just by Jensen's we get E of x min n to the power this. I should probably not. Sorry. I guess I should maybe not write this function. I'll apply Jensen's function to the part P. Figure. So then I need phi of E of x, right? This is my random variable x, this is my phi. So I need phi of E of x. That's going to be equal to E of X with N, the power P1, the whole raised to power P2 by P1, right? And that's going to be less than or equal to E of X. So E of X with N by this is my derivative E to the power P. Okay. And this I know is less than or equal to E of X to the power P2. And now, okay, I can, because this is a non-decreasing function, then they're all bounded, so I can just let them go to infinity. So I get at least that X to the power P1. My modal convergence from this going to this guy. Right? Upon P2 by P1 is less than equal to this.
And that gives you.
And that gives you the norm. But you get to see that this gap thing helps you, so this was very well defined, and now I could apply modal convergence, so I get the existence. So I needed to do this extra work. Take it. Alright. So then is that okay? Okay, so now we're going to prove completeness of LP spaces. So LP space is complete. This point is clear, right? What do we mean by this?
Any Cauchy sequence in LP will convert to some sequence if the sum function is random variable.
So basically,
I didn't get one part actually. Why you use the L2 norm to show the existence of L1 norm?
why do we use?
Yes, I'm trying to say this shows that
Yeah.
if some function is in L2
Then
or then it is L1.
Right.
But that doesn't show the existence of L1 norm, right, for every function. Means, what did you show? I didn't got it.
Well, so I told you upfront that I have a random variable x,
Yes.
which is in L2. So E of x square is less than infinity.
Yes.
Now, a priori, you don't know that E of absolute value of x is finite or not.
So you are assuming that it is in L2, then you are.
That's right. Yeah. If I assume it's in L2, then it should also be everything less than that. Yeah, I mean, we assume it's obvious, but this has to be shown, right? The other way around, of course, not. You can always consider random variable where you at least be a little bit and suddenly.
So for us, L-infinity is some good space or a bad space?
It's a restrictive space, I guess, yeah.
Means there is no such a good example of random variables.
No, it comes up a lot. I mean, if you do, it's a dual of L1 space, right?
Yes.
It comes up, but I guess L2 space is perhaps the most interesting. Because L2 is also a Hilbert space. Yeah. So right now, yeah, we won't spend too much time on L2 space. So LP space means we have in this space we have an idea of a norm. So it's a norm space. We want to show it's a Banach space. So it's a complete space. Yeah. So you're given the sequence xn minus xn, and this is going to 0 as n and n. Right. Now we want to show there exists an x in LP in the same space such that xn minus x. That would prove completeness, right? In this general space. How do we show existence? Do you have a sense of what to see? Yes, because you need a candidate, right? You need a candidate for x and then you show, okay, that's right there.
Somehow using the series part, from the series we can get some of somehow we have to rearrange the series to get some function x.
Yeah, so somehow from
The
the
series.
sequence you have to extract the function x.
Yes, that is.
See, what do I know? These are clever things, but I know that if I give you a Cauchy sequence of real numbers, then they will converge to a real number. That part I don't know.
Yes.
So somehow I need to boil this to that.
So probability distributions
Hmm?
for every word, say P of xn in P and P of xn in B, their difference goes to.
Oh, I see. You want to get it that way. So suppose you had that. Suppose that the probability distributions were converging.
Then we could find a random variable x with xn.
With distributions, you can't find out. I can give you distributions converging on completely different probability spaces. So it has to be in the same probability space. So we have given you a probability space where you have the sequence of random variables. On that space, you're going to converge x, construct x. So is that clear, Daksh, Malhar?
Yeah.
Redmire? I don't know Redmire is probably Shantanu. Okay. All right. Yes. So you need, and what you do is you extract a subsequence. See, right now it's converging in LP. But before I even do this, can you see examples of random variables which are converging in L, let's say L1, but not converging almost surely?
1 by x in 0.
The same example that we're doing, right? So that's converging in L1, not in almost surely. And the other way around, can you construct examples of random variables which are converging almost surely, but not in L1?
Almost surely convergence.
No, almost sure that not at that. Yeah. So can you, even I don't remember it. I'm sorry.
8 times characteristic x between 0 and 1 and
That will converge almost surely.
almost surely, but not in L1.
Yeah, that's right. Yeah. So that's an example of almost sure convergence and not L1 convergence. But now, where's the example where you have L1 convergence but not almost sure convergence?
Like the sequence we constructed on the last.
Oh, that's very good. Yeah, that's very good. You have convergence with probability but not almost sure convergence. In that case, convergence probability for bounded random variables also being convergence in moments.
Yes, and if you get one moment, you will get.
So that example will do. So yeah, so it's true, and this is what we discussed last time, right? That we had convergence in probability, and we could extract convergence almost surely through subsequence. So same thing we'll do here. We'll extract convergence through subsequence. Then we'll see that we are converging pointwise. And on the point, then we can apply the fact that we have a Cauchy sequence on each point that should converge to a real number on that point. So we'll use that practice. So it's good to kind of see this thing. So let's see how do we do this. So I can get you a subsequence x n k plus 1 minus x n k. So I'll get you a subsequence n k. So that this is less than equal to, let's say 2 to the power minus k. Again, I'll do this, right? Pth moment. So I automatically get the expected value of x n k plus 1 minus x n k. That's equal to 1 plus second of pth moment. Right? Now this sums 2 to the power minus k is chosen, so that sums. That tells you the expected value of summation minus x and k. Right. Take it, and that tells you. So what does this tell me in particular? Can you try and guess where you go from here? Dominated. No. I want to somehow come up with the Cauchy sequence on my space. On each omega, I want to know the Cauchy sequence.
X n k omega
Yeah.
forms converges to some number almost zero.
That's what I want to get at. But in particular, what would help me is this. Does somebody here want to take a guess? That because the expectation of a non-negative random variable is finite, The random variable has to be defined. That's all we really need. So now we are doing it. Now you can probably see what's going to happen. Almost should. Right? On a set of measure 0, anything can happen. Now, how do we proceed?
Almost purely omega.
That's it.
That x into omega converges.
Yeah. So it's clear that on each omega where this is finite, you have a Cauchy sequence. X n1 omega, x n2 omega, x n3 is a Cauchy sequence basically, right? Because this omega is finite. So that sequence is going to converge to something. So what I do is, so I know that x and k is converging, I just define lim soup and k goes to infinity. And that's my x. Lim soup because it's defined everywhere. So I don't have to say instead of measure 0, I don't have convergence and I put 0 or something. Okay. So this series, x and k sequence is converting to x for motion. Right?
Like we can write limit here also, right?
Well, on this almost surely. So I could tell you that on a set outside once set of measure 0, I may not have it.
Yes. For the limit, you don't even know it's the limit is not necessarily a random variable, right?
No. I mean, you have to kind of construct. You have to say that, okay, let's say the limit exists of this set. Now, your question is this set measurable? Right? So, as such, I can complete my space and then it will be measurable. So, I know that lim soup of this sequence is measurable. Okay. So, then the set where they disagree, I can, if they're complete, that's a set of measure 0, all sets of measure 0 measurable. So, that would be one way to handle it. Now, I don't know if in this case I can get away with it without doing that. Probably I can. See, lim soup is, no, I can, right? I mean, lim soup is one random variable, lim is another random variable defined. So, wherever they disagree,
It's a measurable.
it's a measurable set here. There's no problem here. Okay, so I got my x now. Okay. Now what I do is I again take, so you give me a k. So I can find a t greater than equal to n of k. Of xt minus x of n of k. To power p is less than equal to c power xt. Right? I'm just going back to my I have this convergence. I have a Cauchy sequence, right? But I'm not going to do this. So and k is you given me. So you give me an epsilon, so you normalize k is and now I use now my claim is that this implies so why is that the case?
By the Cauchy fact, it's a Cauchy sequence. So, given any larger of t, you will find a NK that is as greater than t and that their difference is less than say.
How do I bring x into the picture here?
Like this dominated.
So yeah, that's what I was getting. It's kind of from there, but easy argument is from Fatu's lemma. This is lim inf of xt minus x and k. And that's less than equal to lim inf here. And that's less than equal to 1 minus k. Right, so can you see this just from Fatu's lemma? This quantity will be less than equal to this quantity. So first I fix the k and then I fix this side. So I could have used some other notation for this side, I guess. On this case. So on. So this is fixed now. Now I apply for this lemma. So limit from this is also less than equal to that guy. Limit if I bring inside, I get this. Yeah, but usually the arguments one comes up with tend to be messy. So you need to get kind of familiar with variety of ways function approach a problem and see what works. Okay, now that I have this, so this immediately implies that E of x to RP is less than infinity. Okay. Because E of xt is going to be less than infinity, right? All of these guys are in LP space. So x is LP. So I didn't know this. I just had a candidate x which existed. It was a random variable. I didn't know it was an LP. Now I know it's an LP. And then I come back here. This is K0. So basically, I can always choose my t small enough, t large enough, so that this can be made arbitrarily small. So my sequence xt is converting to x in LP. So I also get that. So I get my set of groups. So there is a candidate random variable x in my LP space, and my Cauchy sequence is converging. Okay. Now what I'll do is I'll look at this L2 space, because L2 is a Hilbert space. So this is my L2 space actually. And I look at a subspace. So K is a subspace of that space. So it's a collection of random variables, it's still a vector space, the subspace of L2 space. But I'll take K to be complete. So suppose I in my L2 space, I have a subspace which is complete. Right? Suppose I have that. Now you say, okay, give me an example of this. Show that your example.
It's constant at some point. The random variables that are constant at 0.
Random variables that are constant.
X0 is always equal to.
Oh, I see. Yeah. It's like all the random variables.
They're always taken as 1 and 0.
What do you mean? So
At some given point.
at some moving variables. Okay. So
But if we take the equivalence class, then
on x in L2. So yeah, it's on a set of zero measure zero. It could be yeah.
On a non-zero measure set.
On a
On a non-zero measure bold set, measurable set, say S, I say x is equal to 0.
on a non-measurable or
On a measurable non-zero measure,
measurable non-zero set, I put it to equal to 0.
and it is constant 0.
And then the subspace, I guess so.
Yes, substance.
Because if I take a linear combination, 2 else will get that. Sure, that would be one example. Yeah. Right. I mean, this could be.
Also, LP measurable for P greater.
Suppose this is some random variable sigma of y. Kappa is. So let's just take. I guess. So for every x in L2, I have a random variable y also in L2. Can I look at the space of E of x given y? So we'll discuss these conditional expectations later, I guess. I connect all these things for each x. So that will be in the subspace of functions which are measurable. That would be another example, I guess.
LP measurable for P greater than 2. Let's say L3 measurable.
L
L3 measurable.
L3 measurable.
That is a subspace of
Y, I see.
But
The other way around probably, L1.5 measurable.
L3 measurable is a subset of L2 measurable.
So if you are L3 measurable, then you have to measure. That's right, yeah. So any L3 measurable would be a subset. That's
but
right.
would L3 measure, I mean, L3 functions be completed in L2 now?
Yeah. So that's the question, I guess. Will it be complete?
Unless they're equivalent now.
I would imagine so. Because if you just go back to the argument that we did, that was true for L3 also. Yes. Yes, that would be complete subspace. But that's a good example. All LP measurable, P greater than 2, that would be subspace. Right? So that's a great
Yes,
example.
but in the argument we had, we are finding the limit function in L2.
So we said that we looked at all the random variables in LP, right? And we found the limit function which is also in LP.
No, he is saying that so when you are in L3,
Yeah.
we are seeing L3 as a subspace of L2.
Yeah.
So yeah, that's true that all L3 functions are L2 functions. But when we are doing this construction to get a limit, that limit is in L2.
No, it's L3. That's my point. That's my point right now. You're given a Cauchy sequence in L3 space, in the subspace. Then the limit will also be in L3. Right? And all of them are in L2 also, that's fine. So I think the proof that we discussed earlier just goes right through. So if whenever you have a Cauchy sequence here, it will converge to a point in this space. In the L3 space.
Suppose how is it's not.
We just repeat everything we did, right? We started by saying let's just look at random Cauchy sequence in L3 space.
Yeah, I understand there will be a limit. Extending a sequence which is both convergent in L3 and L2. Okay.
But we are saying it's convergent in L3.
Yes. So, and since L3 is complete, so there will be a limit.
Yeah.
X.
That will also be in L3.
Yes. And that will also be L2.
Yeah.
X is also in L2 and X also in L2.
Yeah.
But the convergent in L2 function, we will get a limit that is X prime. So how the X prime and X is equal?
Oh, I see your point. No, so the point is, yeah, so that requires, that's an interesting point, I guess. He's saying that suppose that
Convergence if it does not imply necessarily might not imply convergence.
Equal convergence.
I mean, if you are converging to X in L2, then you in L3, then you're also converging to X in L2.
Since both are complete, we have a limit. But
It
how
has
the
to be the same limit. Almost fully has to be.
Right? You cannot converge to
Good
two.
point. That needs to be shown. Go ahead, Mahar.
Yeah, so if you are converting to something in L3, that function is also in L2. Then you cannot converge to something different in L2.
That's right.
The limit is unique.
The limit is unique, basically. If a given sequence is converging to X in L3 and it's converging to Y in L2, then X and Y have to be equal.
So if you want to show we are saying L3 is a subspace, L3 measurable random variables is a subspace of this vector space.
Yeah.
So when you are talking about the Cauchy sequence, we are actually talking about a Cauchy sequence that converges in L2, not in L3.
But limit is
No, I think the way we are going to define right now is we're going to look at Cauchy sequence in this space itself.
Yes,
You're right, we could have done it more
Yes,
generally.
but since the parent space is L2,
Yeah.
the definition of Cauchy sequence will be expectation of xn minus xm squared less than xn.
Yeah.
Right.
So the
And then will
that's true.
so actually
Okay.
it's converges both in L2 and L3.
Yeah. So I agree with you. I think let's just collect. That's a good point. Because we are given a Cauchy sequence in L2. We're not given a Cauchy sequence in L3. So hence the limit is in L2. But if the same sequence will have to be Cauchy in L3 as well.
Yes, it's Cauchy in L2 implies it's Cauchy in L3 because those xn minus xm cube terms will just reduce.
Is that right?
And it mostly it should be less than 1, right?
I mean,
Cauchy in L3.
Cauchy in L3 implying Cauchy in L2, I understand. But Cauchy in L2 implying Cauchy in L3 is not so clear.
It can be different lines, like different subspaces.
Walls are changing,
Not,
right?
it cannot, can be like different subspaces. Like L2 is then where implying that L converting L2 means converting L3. But the subspaces can be big.
Well, I mean, L2 is a bigger space than L3. So I mean,
Yeah.
L2 is the whole space, L3 is this space.
But it's different.
But right now, I think, so let me just make sure I sort of take you down here. Is that's true, extend the Cauchy sequence, and P. No, this is what it is. This is what it is. Okay, yeah. So, I mean, so yeah, I mean, right now we don't need to have that discussion per se. For what I'm going to prove, we don't need to have that discussion. In the sense, when we do look at a subsequence, it'll be clear that we're looking at subsequence in a particular subspace. Right. So does the bigger question still remain that suppose so I mean, if I have a subsequence in L2 and all these random variables are L3, suppose, then they will have a limit in L2. Now, I mean, I guess so. The question really boils down to is that what does the Cauchy sequence in L2 correspond to a Cauchy sequence in L3 or
So I
not?
believe it does, because so for any n and n,
Yeah.
consider the following event, the following probability absolute value of xn minus xn greater than 1.
Yeah.
So it's causing L2 implies that for any epsilon large enough, I have n and n, such that for any n0 m0 greater than n and n, this probability will be less than epsilon.
Okay, hold on. So you're trying to make a case that
Cauchy sequences in L2 are actually also
Cauchy
Cauchy
sequence in L3. L3. So I just want to kind of immediately kind of tell you that that's not true. And that's because, you know, if I just have a arbitrary Cauchy sequence in L2, you know, I can have sequence xn in L2, which is going to 0, let's say. And I can have that, you know. But the same thing, I can always convert this to second sequence. So this is equal to infinity for all that. So this is not good, right? Yeah, so I think so. Your point is valid. I just haven't even, that's not the question I want to face right now. So we will be looking at a sequence which is in the particular subspace. And if you're Gaussian that space, then there won't be any confusion. So where do I want to go with this? So this is some subspace which is closed, which is complete. So of course, the sequence in the subspace converges to a point in that subspace. We are given that. Okay. Now I'm given a random variable x, and my claim is that there exists a random variable y here, which is perpendicular. Right? So just the geometry of the integral holds. That is, if I look at so if I look at infimum of p of x minus say z part p, all random variables z are lying in my space, in my subspace kappa. Okay. Then so there exists a y in my subspace k. I'm calling it k right now. So that is equal to u x minus y.
So what came to it?
We're looking into. So this infimum will exist in the space K. So y is going to be K. And furthermore, so we'll see this. I guess I'm calling it, I'm looking at it this way. Okay. Furthermore, you have this property that E of x minus y into z is equal to 0 for all the in. Okay, so this is any z. If I do it, x minus y times z, that's going to be this line and this line are going to be proportional to each other. This is your idea of a inner product. Okay, so that's the proposal we're going to do right now. So it's very geometric, but I can prove it in this generality. So what do we suggest we proceed? Again, these are again you have to be. It's difficult to immediately guess how to proceed. But at least what you know is that because this is an infimum, I can at least come up with a sequence x minus yn, which is going to converge to, let's call this delta. That's going to converge to delta. And that I can always.
And so y answer for C. For C.
Yeah. So I'll show the y answer. So that needs to be shown. And since no exactly, so once y is a Cauchy, then y is will have a limit 1. And that's my
That's in the subspace because it's.
and that's going to be considered. So in that sense, y's are in the subspace, and the subspace is complete, and y's are Cauchy, there will be a. That's what I get. Right. So how do I show that y's are Cauchy? Yeah. So I mean, you can kind of imagine how you might proceed, but let me just show you a thing. Right? Whatever you're going to guess, let's try this, let's try that.
So, say E of xm minus absolute value of x minus ym is less than or equal to absolute value of x minus ym plus absolute value of yn minus ym.
Right.
So we can value upper bound absolute value of yn minus ym.
No, so I think you're getting the bound in the wrong direction right now, right?
No, I'll get a upper bound on yn minus ym.
How are you getting that?
So absolute value of x minus ym,
Yeah.
norm of x minus ym is less than or equals to norm of x minus ym plus okay no.
You're not upper bounding it here.
Yes, sir.
Yeah, that's it. I mean, you have to be a little bit careful in how to get the. But the argument is similar to what you would have done the gradient setting. So, but it just requires to
Like if it was true, we could apply it to any norms test. Yeah, like what Siddhartha was saying, if that was true,
That's right.
you can apply to any norms.
So you have to use the fact that it's second now. That's a good point. Yeah. Yeah. So what are the special properties of the second now that we can use? That's what I have. So let's just do this. So we have x minus yn plus x minus yn. Right? So we let's just look at the square of this. Square is on the right side, right? So I know for the second moment that a plus b square a minus b square. This is just random variable a square plus b square plus 2 expected value of ab. A square plus b square minus 2ab. This is going to be equal to 2 times a square plus 2 times right? So we'll apply that. That's going to help us basically. That will help us we'll get the equality, not an upper bound. And we isolate yn minus yn, which is what we want. So we get here 2 times this plus this. That's going to be.
Is just a natural formula. There were yn and yn were different.
Minus plus and plus.
With a is equal to a plus b plus a minus b by 2. So I'm taking this plus this by 2. Okay, that's what gives me this guy. And thus I have 2. There's this minus this by 2. X gets cancelled, then I get yn plus yn. Yn plus yn? Minus. Yeah. Yeah, that's right. And now we are kind of much better shape. So you know that this is going to delta. This is going to delta. This is greater than equal to delta at least. Right? Delta is in theme of, because yn plus y by 2 is in my subspace. So this is at least delta. So the square delta square. Okay. So that tells you that okay, yn minus yn is basically a Cauchy sequence. Okay, just from there. That's why yes, y minus y is a Cauchy sequence, so there exists a y. Y minus y. So we could not do this when we had space.
So any p not equal to 2, this is not.
Yeah, that's what I was also thinking. I mean, right. I mean, certainly the idea of projection should be well defined, right? So if I have any x and I'm projecting into some space, some convex set, that should be well defined.
You might not get the equality.
I mean, you won't get that perpendicularity condition.
Yeah.
Otherwise, you know, if I have a convex set at this x, there will be a point which is closest to it. That existence I can get.
So if you just see the balls
Yeah.
in around 0,
Yeah.
only in the L2 node, it will give you a circle. But in other case, it will either give you a ellipse, or in the L1 node, it will give you a strip.
Oh, that's right. Yeah.
And in the P1 node, it will less than 1, it will give you an asteroid.
Do you even for less than 1? Do we even have triangular property?
No.
So it's not even.
Yeah, that's why it's asteroid. We don't
Yeah.
know.
Yeah.
That's why.
Yeah. Yeah. So I don't even want to talk about less than p. I don't know what to say right now. But p greater than 1, I think this part will be true that you can always project to it and you get a unique projection. At least if
P greater than
p
1, P greater than 1.
greater than 1, yeah.
And less than infinity.
Probably also p equal to infinity also.
Yeah, it will be also a square.
Yeah. So then also. Okay. So what do we need to show here? So I have of x minus y.
So basically, that separating hyperplane theorem works in LP, right?
Yeah.
Then you will get it by moving that plane.
So projection element, yeah.
Yeah.
No, I think yeah, that will look. The perpendicular property I won't get. The
Right.
second part is. Which I mean you can also see geometrically. Yes, right now I don't want to comment more on the geometry. A little rusty on this thing. Okay, so this is. This is going to 0. This is going to delta. Let's say this was equal to. At least we got that again. Again, it had to be spelled out, but yeah. And now what we want to show is just this part. the fact that your x minus y into z is equal to 0. That is sure. Again, you can show this exactly how you show it in the equation setting. But let me show you in one particular way. Remember this. So I look at so I observe that okay. So again, this is my picture. This is my x. This is my y. Let's say my z. Right. And I want to say that x minus y is perpendicular to this. That do it at take some point here, right? This point here I can write as 5 plus t times z. Appropriately. So x minus y minus t z. Okay. This is the adjustment. Can you now repeat the proof? Yeah.
They'll compute it and we'll find.
So let's compute this exactly. X minus y square is exactly delta square. That cancels. So I'm left with minus, I guess, 2 times e of x minus y. T comes here into z, and then plus t squared x is equal to x squared. Right? And this, by the way, is true for any t, and t need not be positive. So t positive or negative. So now is it clear that this has to be 0?
Yes.
Because if it's not 0, then you have no condition for something.
Equals to minus epsilon.
Because e of z square is going to be positive. If z is 0, then nothing will be moved. Then it's all obviously. So z is not 0, so this is strictly positive. So then the only way you can show this is if t is this point is 0. Okay. This one is some of that. Very nice stuff. Later we'll talk about conditional expectations, and we'll actually use this to prove conditional expectations. And a lot of other existence also can be used in this. I forget now. I don't know, Shubhata, if you remember, radon nicotine theorem. Is it proven using this? And then, so even radon nicotine theorem can be proven using the signal radius. Okay, let's now go back and just finish. I'll talk about this topic we have not done earlier, so let me just go back now. So Kolmogor's 0-1 law. Now, how many of you already know this Kolmogor's 0-1 law? You know. I mentioned last time. But Nick, you heard of this? You not heard of this? Have you? Sorry, forgot. Okay. Malhar, you know this?
No.
No.
No,
Sorry, but is it a no or a yes?
no, I don't know.
No. Okay. Yeah, no, the voice is not so clean. Should come on campus soon. Okay. That should be okay. Yeah, so the point is this. So suppose they are given random variables x1, x2, xc, and so on a common probability space on this, right? So then we can talk about Tn. This is the sigma algebra of sigma xn plus 1, xn plus 2. Right. So smaller sigma algebra which makes all these random variables measurable. So now you can define an interesting object. With this, you can define for each n. So you can also define intersection of these things. Right? And that's again a sigma algebra. Whenever I intersect arbitrarily many sigma algebras, I get a sigma algebra. That's a simple proof. Okay. It's not going to be empty, but it contains the whole space, it contains an empty set. That is it. So what can we say about events in sets in T? So apparently we can see some interesting things when x1, x2, and so on are independent. So suppose the theorem is as follows. Just x1, x2 are independent. Either now is trivial. That is, if A is in no, either U A is equal to 0 or P of A is equal. Right, either it is 0 or its complement is 0. Okay. So what are the events in this T? Let's talk about that first before we start proving this theorem.
C is probability for xi
T is a sigma algebra, right?
yes. P is
Oh, P is a probability, yeah. So there's always underlying probability space here.
xi are not necessarily identical.
No, just independent. Just independent. And independence requires a probability value, right? So independence is not independence of the probability.
Yeah.
Right. So before we go there, let's ask. See, basically, what is the sigma algebra T? It's all the events which depend upon infinitely many xi's. Right. So, for example, we saw this event.
Do not depend on any finite value.
Yeah, that do not depend on any finite value. They depend on finite infinite. Infinity of. This event, you can't observe finitely many xi's and say that you know that event belongs to sigma. It doesn't belong to any sigma x1 through xm or any. So those kind of events are going to belong to this sigma algebra. Basically, this event is same as xn is greater than equal to 2 infinitely often and n is greater than equal to n. That means this event belongs to and it belongs to T of f for every n. And hence it belongs to intersection of T of f. And hence it belongs to T. Okay.
I just confused why tau is not in.
Well, it's not empty because it at least contains the overall space omega and it contains empty set. Because each of the sigma algebra contains the overall space omega. So whenever I intersect sigma algebras, I won't get an empty space. I will get a sigma algebra. Right. Okay. So it has to be in each. It's a fascinating object. I mean, after if you know it, you know it, but if you don't know it, it's quite the first time it's very interesting to come up with. But in some sense, as we saw, when Borel can tell you, either the probability was 1 or 0. So it can set your mind that is that always true? And under what condition is it true that the probability is either 1 or 0?
Borel control is the special case of this actually.
Yeah, exactly. But I'm just saying that that's probably how one starts thinking about this. One begins to wonder, okay, maybe the bigger it is. let's see. Suppose I say to you omega such that okay, x1 plus x2. Momentum goes to infinity. Exists. So this is also set of omegas, right? Where this term is. So this set will also belong to your term. Because it doesn't depend on the first few pairs. So I can always kind of change this and say, okay, listen, it's so the limit will be same as x n plus 1, x n plus 2, plus x n plus n, 1 n. If this limit exists. And this belongs to my. And I can do this for each n. So I'm talking about the same set basically. And the same set belongs to each of these sigma elements. Hence it belongs to the set. So similarly, I can talk about the random variable again. Random variable limits to n goes to infinity. So this random variable y will be now measured. Because again, it's going to be each measurable is going to tau for each n. So it will also measure this. So this is a sigma algebra which contains all these events which depend on infinitely many random variables. And you can say something about the random variables which are measurable with respect. So the theorem now is this. And I've already stated the theorem. So the theorem is each event has either probability 0 or 1. Hence, if random variable, if y is measurable with respect to the sigma algebra, implies that y is deterministic. That is, there exists an x, so that probability that y is equal to y. It takes only one value. Now this y could be minus infinity or plus infinity, limits to common can be this thing. Or it can be a positive number. That's the theorem basically. Okay. How do we prove this theorem? Again, you'll have to see this. You can't guess the steps. I mean, again, I've said this before, but I said again, this is one subject where it's difficult to guess the steps often in many problems. You have to know them. Otherwise, people struggle for a long time to figure things out. But what we show is as follows. Basically, we show that sigma algebra tau is independent of sigma algebra tau. So it's an odd statement, but we'll show that the sigma algebra is independent of itself. So probability of any event A belonging to the sigma algebra is equal to probability of A intersection A. And because they are independent, this is P of A squared. And hence P of A. It's one of those proofs that you want to hit on its head, right? It's very unsatisfying. There's no kind of intuitive content to it. There must be, I don't have it. When you look at it, you have to ask yourself, okay, it's got to be better than all these things. Yeah, no, but I'm not aware of this. I mean, when we do martingale, we again see this, and there's another proof which I forget now if it's more intuitive. Huh? Reverse martingale. Yeah, I mean, reverse martingale, nothing is intuitive. You get law of large numbers proof in one line. Just one line. Oh, you have to build up the machinery for it, but it's just one line. All you want is the moment exists, single moment exists of each guy, and then you get the law of large numbers. If you see an actual proof for a single moment, so I'll show you law of large numbers right now for independent random variables when fourth moment is bounded. And that's a fairly simple proof with 4 or 5 lines. I'm not sure. Yeah, we've not discussed that so far. You probably Seen it already.
No, no, we have discussed it, but not.
Yeah. But when you assume that all these guys have the first moment existing, other moments may not exist, then law of randomness is actually quite a demanding proof. But the reverse Martingale is for that. All right. So what do we do? Yeah, what we'll do is we'll look at sigma x1 through xm, right? And sigma xm plus 1, so on. So these are obviously independent, right? An event here and an event here, probably the assigned them is just going to be third of the problem. So they are obviously independent. Now, right. What that means is that this guy is independent of, because tau is just a subset of this. This is independent of from, right? That's clear. Now I look at the algebra. This union of all these sigma algebras, right? That's no longer a sigma algebra, right? We know that. But it is an algebra and it's a pi system. And that is also independent of this pi system. And it's a sigma algebra, it's also a pi system.
It's also pi system.
It's also a pi system, right? So because now you know, so what was the result that if a if you have this independence of two pi systems, you have independence. If you have, probably, if you have independence on sets of two pi systems, then you also have independence of the sigma algebra containing this. Yeah, exactly. And now the sigma algebra containing this is exactly sigma x1, x2. Right? So that is independent of. But this contains tau.
The T component.
So this is what it is.
It makes no implication.
Huh?
It makes implication.
It makes intuitive sense. Some intuitive sense is there.
Makes no sense.
Makes no intuitive sense. I thought you would say some intuitive sense in there. Let's not spend time on this. Yeah, I mean, makes no intuitive sense, you're right. Very difficult to get any kind of prediction from this. We looked at the union of these guys, and suddenly we are looking at events whose limit is going to be down. Right? And we said all these events were independent of tau, so the limit is also going to be independent of tau. The limit is those events itself. So that's how one can try to get intuition, maybe get a clearer picture of this.
Will follower to be destroyed only, or even if you put them.
No, this is a word when I read up to teach, but I don't spend time thinking about it. My time is, one can do very interesting things with probability, so-called the field of applied probability, which is not really that applied, it's still going as deep, very deep probabilities. But certainly deeper than what we see in very computer science. You don't like that sentence. No, it's still probably true. I mean, it's not kind of thinking at the level of cosmography, that's pure probability. But I think the kind of terms that kind of moves using the tools of probability can be quite deep. Let's just say we're thinking of different things, but this is not the kind of stuff that. So I don't go back and see, okay, let me see Cosmograph's paper, or what did those guys were doing. Also, I guess in some sense the fields always move on, right? So what has already happened, you kind of don't think
How did someone think of this?
I think it's obvious, right? In a way, once problem suggests itself, then you start looking for it. And now your point is how did one come up with this proof? When you have,
How does someone even think that all k elements will have probability 0?
so once you have Borel-Cantelli, like I said, once you have Borel-Cantelli kind of results,
Okay.
and you have few more results which are proved with great difficulty, but you are ending up with 0 and 1 results. So the question is there. You have a very concrete question to think about. So that's, I mean, often that's the main thing you have to formulate a very nice concrete question, which is unresolved. I mean, you know how we do research, right? You come with a concrete question which you don't know the answer to, and then you come up with a much simpler concrete question which you don't know the answer to, and then you keep on trying that, and you finally solve for something completely else, completely different. That's how research goes. Okay, so what are we going to do now? Yeah, now we'll do the law of mathematics, simple law of mathematics. Alright, so now we are given random variables x1, x2, and so on, independent. Exi is equal to 0. If it's not equal to 0, you subtract them from it, so you make it equal to 0. And then I will assume that okay, e of xi to the power 4 is less than equal to some constant k. Now I want to prove that under these conditions, Sn, which is summation xi, I will go to n. Right? So Sn by n is going to converge to 0. So if indeed I had, if my xi was yi minus mu, u of yi is equal to mu, then what this means is that the summation yi upon n is very clean. Right, so that just follows from here. All right. So how do we show this? So this is essentially a two-line proof, because so when I look at the fourth moment of Sn, take it. Now in this I'll have x1 to the power 4, x2 to the power 4. Whenever I have one xi with single power, that expectation is going to be 0 because all the random variables are independent. So those cost terms are going to be 0. So I just have to worry about the power 4 term. So this is going to be summation I equal to 1 to n u of xi to the power 4 plus I guess summation I less than j xi square x g square x square. All the other terms are 0. Right? And now I can get any of these things. So help me with the remaining steps. This is something we can actually easily. So I want to bound this. Oh, we should stop. Sorry. We can stay for 2 minutes, right? Yeah, let's stay for 2 minutes.
So we have to use the JSS here, Cauchy square.
You could, I mean, in the sense that what I given you is this, right? So somehow you have to use this part, basically.
Yes.
So then you can use the fact that okay, e of xi squared would be less than equal to square root of 3. Because of
So we have this inequality that e of y square is greater than equals to e of y whole square. So e of xi squared will be at most square root of e of xi power 4.
and this also follows from the monotonicity of the LP.
Yes. Okay, causes for this.
Yeah. Fourth moment. So we get this part, right? So then this tells you that okay, when I take the expectation, they're independent. So I get k term upper bound here. I just have to count these guys. So there should be a 6 here. 6 here, right? No, this is fine. This is the final, isn't it? Now I have to count it. Maybe there should be a 2 here, right? No, I less than j, so yeah. Both zeros and nines. Okay, so now. Okay, I think it's going to be. Basically, I'm choosing 2 out of 4, right? So 4 choose 2. That's 6. So it's going to be n into n minus 1 by times 3. 6 by 2. Yeah, no, I think I should have kept a 6 here. Because yeah, in this case, at this point I've already chosen.
Yeah.
When I and j when I'm choosing, I can same I and same j 4 different places, so I'm choosing 2 of them. So I can do that in 6 different ways. Each I and j I can pick in 6 different ways. And now this is going to be I less than j, so that's n into n minus 1 by 2. So that gives me 3 into n minus 1 and add 3 here. And then this is n times 3. Main thing to observe is that this is going to be of order n square. And what I have here is order power 4. So order, see, now that we discuss this.
Marco.
So yeah, we could go in that direction. We could, but it is a simpler process than that. So then you go to probabilities, and from probabilities you know the rule. But simpler
Divide by n square, right?
Hmm?
Divide by n square.
This of course I can just say 3 n k minus n square is 3 n square k. Then of course I have here. I divide by n square.
Yes.
So I get. Yes, that's a much simpler proof. Sn by n to the power 4 is less than equal to 3k by n square. Now I can sum up these things, right? So I get okay. E of summation Sn by n to the power 4 upon n is less than infinity. Okay. That tells you that this summation is less than infinity almost surely. And the only way that's going to be less than infinity if Sn by n to the power 4 is going to 0.
Yes.
And the only way that's going to go to 0 if Sn by n is going to 0.
So if the second movement for this summation would not be.
Yeah, summation. Actually, yeah, one could maybe do it for 3 plus epsilon. 3 plus epsilon would be okay. Alright, any questions? Chalo, so then we meet on Friday. We'll do conditional expectations. Alright guys, have tea on your side.